Okay. So, SPDF, right? Different types of orbitals. An S-type subshell can have one orbital. Actually, I guess they're subshell types. So an S subshell type will have one orbital. P will have 3 orbitals, D5 and F7. And remember, when we talk about orbitals, we're talking about, I think, 2 things. We're kind of talking about a space about the nucleus where an electron's going to hang out. It's a spatial thing, but it's also an energy thing. Okay? So with regard to spatial things, all of the S-type, whether it's 1s, 2s, 3s, or whatever, all of the S-type orbitals in the S-type subshells are spherical. P or dumbbell, and then D gets weird, and F gets even weirder. Okay? So I'll kind of show you what I mean, starting out with the S-type. There's a couple different ways to kind of think about a spherical distribution around the nucleus of the electrons that are hanging out in an S-type orbital. One of them is this, where the nucleus is kind of hiding right there, and kind of this is the distribution of electrons. Another one is, again, the bullseye would be the nucleus, and you kind of see the distribution of the electrons. And here, this is kind of an S-type. These are all representing spherical S-type orbitals. Okay. Then, this is kind of also similar. When you see this dot, dot, dots, that's representing, kind of makes you itch, that's representing where the electrons are, okay? Kind of different ways. So that's S-type, they're spherical. So hopefully you can kind of see that. So, but any principal energy level, N, they always have an S. Now, only beginning with N is equal to 2 do you pick up the P. When N is equal to 3, do you have the SP and the D. And when N is equal to 4, you go ahead and pick up the SP, D, and F. So we need to account for the different the different spherical orbitals around the nucleus. You know, these are where electrons are hanging out. So actually, 3s electrons are spherical, but they're farther from the nucleus. Okay, this is 1s, 2s, and 3s. So they're all spherical, though. The other one, which isn't too bad to explain, would be the P-type. Okay, so this is the P-type. It's dumbbell shaped. Now, you might not be able to tell it, but actually right there between those two humps would be the nucleus. So this is kind of showing the dumbbell would go underneath here and underneath here. Okay, this is another way to look at a P-type orbital. Orbitals in a P subshell. Okay. So the cool thing, I think, is it has, and we're going to call it a node here in a minute, but actually that's where the nucleus is, okay, and these are electron clouds representing one box, one orbital of where the electron's going to be hanging out. But where the nucleus is, there is a 0 probability of finding the electron in a P-type orbital. I think that's it. Okay, so there's one of 3 P-type orbitals, okay. So there needs to be 3 places to put electrons. 3 sets of electron clouds because there are 3 boxes. Okay? So there's a px, a py, and a pz. So if you're familiar with an xy coordinate system, then you know probably that there's actually a z to make it 3-dimensional. And so actually each one of these represents one of the 3 boxes that we can put electrons in. A pair of electrons, if it's completely filled, a pair of electrons, a pair of electrons. So 6 electrons can be represented there. So sticking with the P-type subshell, okay, there you have a piece of X, piece of Y, piece of Z. You combine them, if you have 6 electrons all in that same subshell, of course we would call those orbitals, those 3 orbitals, degenerate. Okay, and if you have 6 electrons hanging out, that's what they look like. It's kind of cool. I said D is weird and F is even weirder. So I'm going to show you the 5 regions of space that the pairs of electrons, if they're occupying the orbitals in a D-type subshell, will hang out in. This is one of them. This is another one, another one, another one, and another one. And at my desk, I was like, well, they look like the same, but if you look at them closely, they are describing different planes. Okay, so we can have an X. This one is the XY plane. This one is also the XY plane, but it's tilted with regard to the origin, and this is the XZ, okay? So they are all unique. And so if you were to kind of, I think this one puts them all together. So there again are the D, the 5D. Okay, just weird, 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 weird. But these would all be representing degenerate orbitals. A pair of electrons can hang out. And those little lobe things there are where spatially the electrons in that particular subshell are hanging out. So just to kind of summarize, we talked Monday that the principal energy level n is equal to 1 will only have one type of subshell, and it will have one orbital, so we'll have 1s. Principal energy level n is equal to 2, we get 2s, 2p, n is equal to 3, we get 3s, 3p, and 3d. And so that's kind of what we've got going on here, shapes. So I mentioned the nodes, okay, and actually that is not any small thing. You really get into studying electron configurations. But as it turns out, any p-type subshell with its 3 orbitals, actually there are 3 nodal planes. So just to kind of finish things up, this is actually my only slide for the 7, right? When you get to F, you got 7 boxes, 7 orbitals. This is one of them. Weird, eh? All right. So on to part 2, and I know how far I want to get in part 2. We won't get to an assignment slide in part 2. I hope you're not disappointed. We will definitely on Friday get to that assignment slide at the end of part 2, and then go on to part 3 after we go over your exam. Okay, so part 2, finding homes for those electrons according to the rules that we talked about. So I mentioned that actually we are going to find homes for sets of electrons as those electrons are hanging out in their ground state versus their excited state. As I was looking at, I know some of you getting ready for the test are working those problems at the end of Unit 3 lecture, which is great. But don't forget your vocabulary. I know this is Unit 4, but just remind me, Unit 3, don't forget your vocabulary. And I noticed that not represented in those problems at the end of Unit 3, not represented is a heat of formation problem. So they don't, I noticed they don't cover all the different types of problems. So you're going to want to get ready for tomorrow's exam. Make sure that you look back at the prior problems. Okay, so we're going to find homes for electrons. Okay. Now you're probably familiar with something called an arrow diagram. And that's what we're going to use too. And actually, when you use the arrow diagram, or if you have used the arrow diagram, or even if you haven't used the arrow diagram, it honestly kind of sets you up for what's called the lowest n plus L rule. And I brought this in here to remind you what is n and what is L. So n, of course, is that principal energy level. N is equal to 1, n is equal to 2, and n is equal to 3. What L we said, and actually this is my first semester to kind of use this word term cross-reference, but what you learned as S, P, D, and F, okay, actually, I should do it this way. This is the way it was done on your notes for Monday. They actually have L values, okay? L is equal to 0, 1, 2, and 3. Sorry, that's a little sloppy. Okay, so that's the L value. So then what this means is when we start to identify subshells, for instance, the 1s, okay, 2s, wow, 2p, 3s, 3p, 3d. I'll show you what this means. For instance, the 1s subshell has a value, n is equal to, of course, 1. And the S value is equal to 0. Yeah, the L value is equal to 0. Okay. A 2S subshell has an N value of 2. The L value, since it's S type, is also 0. So that's what we mean by taking a subshell and assigning an N plus L value. So of course 2P, again the N is 2, and the P corresponds to a value of L is equal to 1. Okay, the 3s, n is equal to 3, okay, and if it's S-type, that corresponds to an L value of 0, okay. So here we have, and we'll talk about this actually probably on Friday, but here we have 2 subshells with the same N plus L value. That's what we're coming up with over here. 3p, so N is equal to 3, and the P corresponds to an L value of 1. Okay, and 3D, of course, N is equal to 3. The D value corresponds to an L value of 2. Okay, I'm going to go ahead and I do want to do just a few more to show you something that we're actually going to hit for sure on Friday. 4s would be what? 4 plus 0. 4p would be 4 plus 1. 4d would be 4 plus 2. 4f would be 4 plus 3. Okay, so here's the deal. Do you see the overlap? Let's see if I can get a different color. Between the 4s and the 4p. Okay. Snuggled kind of between the 4p and the 4s is the 3d. And so actually our arrow diagram fixes that. So I don't start sweating and saying, how do I post N plus L? That's why we use an arrow diagram. Okay, N plus L. Okay. So subshells with N plus L values, and it's called the building up or off-bow method. We're gonna start with the lowest N plus L value and build up from there. Okay. Now, in the event, and we saw it just a minute ago, in the event you have a couple subshells with the same N plus L value, it happens, you go with the lowest N first. Okay? And this here about the guideline, we need to follow all the rules we talked about Monday, basically. For instance, one of the things that I haven't talked about yet, again, that we talked about Monday, is that if you put 2 electrons in the same box, by golly, they better have opposite spins. That's the sort of thing. Okay. So we're going to use the arrow diagram, and it's going to end up making a kind of what we call a building up method. At the end of this part, on Friday, I'm going to kind of show you how to use the periodic table to kind of quick and dirty knock out how electrons are configured around an element. Okay, so starting with the simplest element, okay, hydrogen. We're finding homes for electrons, so hydrogen's atomic number of 1 has 1 proton, it has 1 electron. So this is actually where the electron can go. Actually, right there. But these are kind of the energy levels that single electron have available to it. All right, things get a little more complicated. Anytime you have 2 electrons, so anything other than hydrogen, the energy levels the principal energy levels have a little bit of split to them. So notice there's kind of no split. The main principal energy level, N is equal to 2, N is equal to 3, there's only 1 electron. Multiple electrons, you get a little bit of a split. So Z is the atomic number. Lithium has 3 protons, it'll have 3 electrons. So these are kind of where those 3 electrons can be in their ground state and their excited state. Sodium has 11 electrons. Then going up to something that has a few more electrons. Potassium has 19 electrons. And do you remember a little bit ago when we identified that the 4D and the 3P have the same N plus L value? Okay. So actually, I didn't say that right. Now, the 3P and the 4S, sorry. No, I did say it. 3P and the 4S have the same N plus L value. Here's where actually the 4s slips in with a little bit lower energy. And again, this is reflected on your arrow diagram than the 3D. So this is to say those 19 electrons around a potassium atom are going to occupy this subshell and then that subshell. Okay. So don't sweat it too much, but that's what it does. So there's 2 ways to represent how electrons are hanging out, how electrons are configured. We're going to cover both of them this morning, and then that's about it. We can use what's called the box and arrow notation, where, of course, arrows represent electrons, and boxes, like we talked about, represent orbitals. Box and arrow. I call this the hand cramp way, okay? And don't forget the spin actually should be represented in the direction of your arrows. All right. So going down, okay, these are the first 4 elements. Okay. 1 electron, 2 electrons around helium, 3 electrons around lithium, 4 electrons around beryllium. Now, if you are asked on a homework or on a test to show the electron configuration using the box and arrow notation, you have to do this. You have to cramp your hand. The other thing is you have to, and this is, I run into this with students all the time, you have to, underneath the box, say what the box represents. Maybe it's not so obvious. So, put another way, if you don't have these designations, it means nothing. I have no idea what you're talking about. Those things I scribbled out must be there, okay? Okay. I think your textbook, and I say later on, I'm pretty sure, but your textbook calls, I call them box and arrow diagrams. Your textbook calls them orbital diagrams. Okay, so boron has 5. So excited, we get to go ahead and put an electron in the P subshell. Isn't that fun? Okay. Now I'm going to have to explain carbon. It's something called the Hund's rule. So beyond boron's 5 electrons, carbon has 6 electrons. So the first 5 go here, and instead of shoving in the same box, in the same orbital, it scoots over in the same subshell. Degenerate orbitals, right? And it's called Hund's rule, and it's like, they just like to spread out if possible. They won't spread out to the point of going to a different subshell, because that's a different energy. But if they have degenerate orbitals, like a P-type subshell has 3 degenerate orbitals. They each one have their own room if at all possible. Not only that, but they will have the same spin. Okay, it's like having a house with kids, and if possible, you give them their own room. Okay? So that's an application. Carbon is the first place we get to go ahead and have an application of Hund's rule. So optimize the number of unpaired electrons. But don't go on to the next subshell. Okay, you've got to fill that subshell. In fact, we're going to see that with, let's see, carbon, nitrogen. We're going to see that with oxygen. Okay, so picking up where we left off. Oh, sorry. A little bit of definition then. If somebody says that orbital is paired, that means in that box or in that orbital there are 2 electrons, of course, with opposite spins. If somebody says that electron is in an orbital but it's unpaired, that means it's by itself. Makes sense? And there are some cool things that happen with unpaired electrons. Okay, so nitrogen is 1 beyond carbon. So there are the 6 from carbon, and of course, according to Hund's rule, we go ahead and just spread out. Pick up an electron, or a proton and electron with oxygen, and we're not going to go any further beyond the 2p. We're going to go ahead and start buddying up, just like you would do if you had kids in a house. You're like, dude, we're not buying a new house. They'll share a room. But you better have opposite spins. Okay, fluorine picks up 1 more electron. One of the cool things I think about, and I'll put this other one up here. One of the cool things about electron configurations, I think, is, for instance, if you know the electron configuration of oxygen, and fluorine is just 1 after oxygen, you just got to add 1 more electron. Does that make sense? I just think that's fun. It's like hopping across the periodic table. Not for, well, actually, I don't think it'll be too long. But some of you know that actually the rare gases, and neon is a rare gas, has that complete, what we call octet. And it's exciting because this unit of material we're going to talk about how atoms join to make compounds, and atoms are looking for that octet. So by octet, we mean 6 plus 2. Sometimes, in fact, on my slides later on, sometimes this is referred to as NS2NP6. I can draw today. and S2NP6. All right. Very good. Okay, so let's look at those same, I don't know if you guys can see this. It's kind of grayed out. I'll kind of make it darker in here. Let's look at those same first 10 elements. Now, the difference between that other notation, box and arrow, this is called spectroscopic notation. And I know it looks like you're trying to jot them down, which is good. And it feels like you're getting hand cramp, but honestly, without having to draw the boxes, it's easier. But it's still the same electron configuration. So as you're kind of drawing that, I'll point out a few things that are probably pretty obvious. But for instance, if you pick on any element, we'll pick on oxygen. If you want to know how many electrons are being represented, you just add the superscripts. So of course, 2 electrons in the 1s, 2 electrons in the 2s, and 4 electrons in the 2p. 2 plus 2 plus 4 is 8. Okay, so it's kind of a nice check. The little superscript should add up to be equal to the number of electrons that will be represented, which, in the case of neutral atoms, is equal to the number of protons in the nucleus, which is its atomic number. The other thing that we could pick on carbon, because carbon we said was where we start to apply Hund's rule. To me, the spectroscopic notation, it's missing a little bit of information, sad face. Okay, so that's to say that actually those 2 electrons look like this. Okay, I know it's kind of ugly, but those are my little arrows. These are my 3 degenerate orbitals. This is an application of Hund's rule. So this actually makes up a good point. If you're supposed to draw the box and arrow diagram for the electron configuration of carbon, you need to put the degenerate orbitals too, even if there aren't electrons there. Sometimes students don't. Whole complete set. All right. And that is that. I guess I didn't even get the arrow diagram today. At my desk, I'm like, yeah, let's just wait till Friday. Okay?